Hello friends, I am Bodikar Chetan from NB Mehta, Valwada Science College, Bordi. In today's lecture, we shall study about chemical kinetics, which is a part of Basic Chemistry, Paper 2, Unit 2. Now, before starting with chemical kinetics, let us try and understand what do we mean by physical chemistry. Physical chemistry. So we say that it is a branch of science which deals with application of different theories and laws of physics to chemical system, and it is also concerned with interaction and transformation of material. Chemical kinetics. Now the question arises, what is chemical kinetics and why we should study chemical kinetics, that is, what is its importance and which reactions are studied under chemical kinetics. So answers to all this question will get in this lecture. Kinetics is a branch of science that deals with study of rate of reaction and factors affecting the rate of reaction. Now, rate of reaction is defined as either increase in concentration of product or decrease in concentration of reactant. Unit for rate constant is moles per dm cube per second or kilopascal per second for gases, or it can be Newton per meter square per second. There are various factors which affect the rate of reaction. They are concentration of reactant, temperature of reaction, and presence of catalyst. Kinetic study of a reaction involves three stages. The rate of reaction is determined accurately. The dependence of rate on concentration of reactant is established. Data obtained from the above two steps is used to establish the mechanism of reaction. Chemical kinetics has biological importance. In our body, protein molecule called enzymes, which increases the rate of many biological reactions. With the help of chemical kinetics, we can determine the rate of such reactions. Also, chemical kinetics has environmental importance because we can also determine the rate of formation and depletion of ozone layer. Some reactions are so fast. For example, neutralization reaction between HCl and NaOH, and some reactions are so slow that it may take months to complete. But between these two extremes, there are some reactions which takes place at moderate and measurable rates at room temperature. Such reactions are studied under chemical kinetics. Rate law is defined as experimentally determined mathematical equation that expresses the rate of chemical reaction in the terms of molar concentration of reactants. Consider the reaction A plus B gives product. Then rate equation can be written as R equals to K into A raised to X into B raised to Y, where A and B are considered as concentration of starting material. X and Y are order of reaction, K is rate constant, and R is rate of reaction. Rate constant. It is defined as the rate of reaction when the concentration of all the reactant are unity, that is, concentration of reactant A and B is equal to 1. At that time, we can say that rate of reaction is equal to rate constant. Unit of rate constant is unit of rate of reaction upon unit of concentration of reactant. Rate of reaction can be measured by two methods, physical method and chemical method. In physical method, physical properties like refractive index, conductance, color of reaction mixture, optical rotation, volume of gaseous product formed is measured at regular interval. For example, the rate of decarboxylation of carboxylic acid can be determined by measuring the volume of carbon dioxide gas evolved at regular interval. So we have to keep on checking the volume of carbon dioxide at regular interval. In chemical method, a definite volume of reaction mixture is pipetted out at regular time interval and titrated with a reagent solution of known concentration. For example, rate of acid catalysis hydrolysis of methyl acetate can be measured by titrating the acetic acid formed against the NaOH solution of known concentration. In this reaction, methyl acetate is mixed with water in presence of hydrochloric acid, and the product formed is acetic acid methanol. Now how much amount of acetic acid formed is calculated by pipetting a fixed volume of solution from the reaction mixture at regular time interval, and then it is titrated with NaOH solution of known concentration. The amount of NaOH used up will be the amount of acetic acid formed. If we compare chemical method and physical method, then chemical method requires continuous monitoring of progress of reaction and is slow and time consuming. Due to this, physical methods are more preferred. Next topic is order of reaction. It is defined as sum of all exponents to which the concentration or pressure are raised in the rate equation. So in this equation, order of reaction is x plus y, where x and y are the exponents.
Order of reaction has to be determined experimentally. It changes with experimental conditions. It can be integral or fractional. It can be zero. It changes with concentration, and it also helps to understand the mechanism of reaction.
Next is molecularity of reaction. It is defined as the number of molecules taking part in the step leading to reaction. Consider the reaction A plus B gives product. In this case, two molecules are involved, so we say that molecularity of reaction is 2. Molecularity of the reaction we determined theoretically. It always remains constant and is always integral. It cannot be 0. It does not changes with concentration, and it does not gives us any idea regarding mechanism of reaction. Here are the few examples for order and molecularity of reaction.
First order reaction. A reaction is said to be first order when rate of reaction is proportional to the first power of the concentration of reactant. So let us derive integrated rate equation for first order reaction. Consider the following reaction when A gives product. Initially, when time equals to 0 second, concentration of reactant is A moles per dm cube, and concentration of product will obviously be 0 moles per dm cube. After time t seconds, if X amount of product is formed, then concentration of reactant will be A minus X moles per dm cube. Is directly proportional to the concentration of reactant. So rate is directly proportional to the concentration of reactant. Now what is rate? Either increase in concentration of product or decrease in concentration of reactant. So I'll write this in terms of product, that is increase in concentration of product. If I remove this proportionality sign, I'll put one constant, that is K. We call it as rate constant. And concentration of reactant after time t, it is equal to A minus X. Now I'll try to rearrange this. I'll bring this A minus X on this side, so it becomes 1 upon A minus X, and dx is as it is, and I'll take this dt on that side, so it becomes K into dt. Now I'll integrate this, so it becomes 1 upon A minus X into dx. k into dt. Also I'll apply limit. Initial concentration of product was 0 and finally it reached to x. Initially time was 0 and finally reached to t. Now integration of 1 upon a minus x, it is equal to ln of a minus x, and derivative for minus x is minus 1. Also I'll put limit, that is 0 to x, and k into what is integration of dt, it is only equal to t, and 0 to t. Then I'll upper limit minus lower limit. Once in place of x I'll substitute x, and in second time I'll substitute 0 in place of x, so it becomes minus ln of a minus x. So this is upper limit minus lower limit. Now I'll substitute 0 in place of x, minus ln of a minus 0. Over here upper limit is t and lower limit is 0, t minus 0. So finally it becomes ln of a minus x minus minus plus, over here 0, so no value. I'll write it as ln of a is equal to k into t. So I can write it as ln of a upon a minus x is equal to k into t. So I'll bring this t on this side, so it becomes 1 upon t, 1 upon t, and then finally ln of a upon a minus x equals to k. Then I'll convert this ln to log to the base 10. So k equals to 2.303 upon t log of a upon a minus x. So this we call it as integrated rate equation for first order reaction.